7.2 is on exponential growth and decay models. It turns out that mathematical models where the rate of change is proportional to the variable itself, they're really common in both the business and scientific world. So this is what we're talking about, right? If I have the rate of change of y with respect to time, that's dy dt, it's proportional to y itself. To be proportional, what that means is dy dt equals some constant, k, times the variable itself. So what we're saying is these two, dy dt and y, are proportional to each other. So these are really common problems that come up a lot, right? I have the rate of change of y with respect to time equals a constant of proportionality, that's what we call k, times the variable itself. So what we're going to do is use calculus to come up with a formula here. So we're going to take that dy dt equals k times y. This is the differential equation. We're going to solve it. This is what we did in 7.1, right? To come up with a formula. Now, you may actually recognize, we actually, I think, did this probably. If you did number 7 on the last assignment, you actually have already solved this. But I'm going to go through it real quick here. So to solve this differential equation, I'm going to times the dt over the right side and divide the y over to the left side. So I end up with 1 over y dy equals, I left the k over here, but I times the dt up to that side. So I've got my y's on the left side of the dy. K is just a constant. I'm going to leave it with the dt. Now we're going to integrate both sides. So when I integrate 1 over y, I end up with the ln of the absolute value of y. K is just a constant, like for example 5. If I integrate 5, it comes out to be, we're using the variable t, so if I integrate 5, it comes out to be 5t. So if k is a constant and I integrate it, it just comes out to be kt. And then I have my constant out there. Okay, let's keep going with that. So I want to solve for y, so I'm going to take e to both sides. This is really similar to a lot of the problems we've done. E to the ln is cancels out, so I have the absolute value of y equals, remember over here we're going to split this apart. We're going to say it's e to the kt times e to the c1. That just becomes another constant. So I end up with, I'm going to come up over here, end up with a second constant times e to the kt. And then to get rid of the absolute value, we put a plus or minus. But if I take plus or minus this constant, it's just a new constant. Okay, so I get all the way down to there. This is our formula. Hopefully that seems a little familiar to you. This is one you actually use a lot in pre-calculus math 3 when you work with exponential models. So some exponential models you probably should be familiar with or you've seen before. You have the model for money when it's compounded, like interest earned, or future value when it's compounded continuously. Sometimes you refer to it as the PERT formula. This is used a lot to model population. It's used with money. It's used with radioactive material. If you talk about how it goes down, the amount of radioactive material declines over time. This model can be used for all of those. So if you look at what the different parts represent, right? C is the initial value, so it's the starting value. K is the constant of proportionality. Underneath there, sometimes K is also referred to as the rate. So K is the constant proportionality or the rate. This is important. If it's exponential growth, like the amount is growing, then K has to be greater than 0 if it's growth. If it's decay, then K, if it's decreasing, right, decay means that it's getting smaller, the amount, then K is going to be negative. Those are the two constants. So once you come up with a model, you should find C and you should find K, and then you have the model. The Y and the T are your two variables. So as time goes by, Y gives you the amount of the substance at any given time. So if you plug 5 in for T, then it'd give you the amount at 5 years or whatever your unit of time is. So you're not plugging things in for Y and T. When you're finding your model, you're trying to find C and K. Those are two things you have to find. Let's do a couple of examples. This says, what is the rate of growth population in a city whose population triples every 100 years? Assume the population growth can be modeled using the basic law of exponential growth. Hey, when you hear that, the basic law of exponential growth, you ought to be thinking that y equals c e to the kt. That's what it's talking about. And then it wants us to find what is the rate of growth. Hey, whenever it talks about rate, it's talking about k. So I'm trying to find out what k is. All right, so to figure out what k is, I've got to plug something in for c, and then I'll need a t and a y. I have to have everything but k. So let's read through and see what it says. It says the population triples over 100 years. So at 100 years, I know the population has tripled. This is a little bit tricky because it doesn't give us an initial population. So I'm just going to say C is the initial population. So that's the initial population. That means that after 100 years, my future population would have to be 3C. So that's what I'm going to put in for Y. Okay, so let's plug all that in there and see if we can solve for K. So I know that Y, the population has to triple, so it'd be 3 times C. C is the original population. E to the K, and it's after 100 years, so that'd have to be 100 up there. So now we have to solve for K. Well, K is up in the power, so we've got to get it down, but first let's get rid of the C. And this works out kind of nice. If I divide C on both sides, I end up with 3. So now the C's gone. Okay, now I just have to solve that exponential equation. We actually reviewed this way back on Unit 1 when we reviewed some of that pre-calc stuff. But the way I get rid of the E to get the K out of there, is K out of the power, is I take the ln of both sides. So if I take the ln of both sides, I end up with the ln of 3 equals the ln of E to the 100K. Ln of E is going to cancel out. Ln of 3 equals 100 times K. Divide by 100. That'll tell me what K is, and that's what we're looking for. Remember, K is the rate. So let's plug that in a calculator. Let me grab a calculator here. Ln of 3 divided by 100, it comes out to be 0.010986, and it's irrational. It just keeps going there. Now, that's what K is equal to. Now it wants the rate expressed as a percent. This is not written in percent form. So move the decimal over twice. You get 1 point, and it wants us to go to the nearest hundredth. So 1.2 decimal places, 1.09. If you wanted to round it up, you could round it up to 1.10 if you wanted. Both of those will work. Okay, so if it's talking about rate, you're trying to find out what K is equal to. All right, let's look at that next example. Example number 3. It says, let Y represent the mass in pounds of a radioactive element whose half-life is 4,000 years. Really quick, just to review that, you may or may not have seen these problems before, but if you talk about radioactive material and you talk about half-life, that's how long it takes how many years have to pass until half of the material that you started with is left. If I start with 4 pounds, then in 4,000 years it should be down to 2 pounds. So that's kind of what it's talking about with half-life. So this says if there are 200 pounds of an element in an active mine, how much will still remain in 1,000 years? Okay, express your answer to 3 decimal places. Okay, so we're using this is exponential. Instead of growth, it's decay. That means my K is going to come out to be a negative. But let's go ahead and set up our model. So I have Y equals CE to the KT. And let's plug in what information we have. So I know that C is equal to 200. It's the initial amount. And we want to know how much is left after 100 years. Well, the problem is before I can do that, I have to figure out what K is. So we're going to go back and figure that out. You can use the half-life to do that. So we're going to use this half-life of 4,000 years to do that. So I know when T is 4,000, right? When T is 4,000, there has to be half of it left. So if I started with 200 pounds, that means after 4,000 years, there would be 100 pounds left. So I'm going to put 4,000 in for T. I'm going to put 100 in for Y, and I'm going to try to figure out what K is equal to. Now, it's not actually asking me for K, so that won't be my final answer, but I have to find K before I can get my final answer. So let's put 100 in for Y. Let's put 4,000 in for T. Okay, so divide by 200. So if I start with that, so I have a half, 100 divided by 200, right, equals e to the 4,000k. Take the ln of both sides, so I have the ln of a half equals 4,000k, right? That gets rid of the e on the right side. Divide by 4,000 to get rid of that. Okay, this is what k is equal to, right? It's equal to the ln of a half divided by 4,000. Now we want to figure out what that is a decimal, so grab a calculator, and we're going to plug that in our calculators to figure out what that comes out to be. So ln of a half, or 0.5, divided by 4,000. Okay, so my calculator is saying it's negative 1.73286795 e to the negative 4. That means I need to move the decimal place 4 places to the left. So it's like this. K is equal to negative 0.00017. You know, it just keeps going after that. Now, if I round that off, that's going to cause my second answer that I'm going to have to find here to be inaccurate. So what we can do instead is I want you to store that in your calculator. So to store that, if you have a TID4, down in the bottom left-hand corner, right above the on button, it has the store. So go the ln of 0.5 divided by 4,000, get the answer on your screen, hit the store button, and it'll come up with answer, arrow, and you pick the variable you want to store it as. I'm going to store it as k. So I'm going to hit alpha k and hit enter one more time, and it should bring up that answer again, which means that it's successfully stored it. All right, so we're going to take that k. So now up here, come back up to my model, which is right here. We were missing k. I'm going to leave it as k, but just know that I know what k is equal to. And again, this will make your answer accurate. If you round this answer off right here, it's not going to be an accurate answer. So it's really important when you find k, use the store button in the calculator to find that. Okay, so now I've got my model, which is right here. I know what c is, and I know what k is. Now I'm ready to actually answer the question. So the question is, how much will remain in 1,000 years? So I'm just going to plug 1,000 in for t. So my calculator, I'm going to have y equals 200 e to the k times 1,000. Okay, so grab your calculator, plug that in there, and we're knowing again k. We know what k is. K, the calculator knows what k is, right? We stored it in there. So it's 200 times e to the k times 1,000. Hit enter. I got 168 point, let's write this down. So we want how many pounds? So y is equal to 168, 3 decimal places, 179 pounds. Okay. So in these problems, what we're looking for normally is, can I find c? Can I find k? Those two things. And once you have that, you have your model. And then, you know, if they ask me how much would be left in 10 years or 1,000 years or 5,000 years, I'm just going to plug that in my model. Or it could say, hey, how many years would go by until you'd have, you know, 100 pounds left? Well, I'd plug 100 in for y and solve for t. But once you have your model, you know, if they give you a t, you can find y. If they give you a y, you can find t. So we're always looking at that and trying to come up with that model. Okay, let's look at example 4. This one's a little bit trickier. So we're going to do a Newton's law of cooling. And what it says is that the rate of change of temperature of an object is proportional, so that proportional is important, to the difference between the temperature of the object and the temperature of its surroundings. So it's proportional to the difference between the temperature of the object and the temperature of its surroundings. So we just talked about that whole relationship between the rate of change and a variable, and if it's proportional, then we can set up that whole relationship. So let's write this down. I'm going to say this. I'm going to say dy dt, the rate of change, is proportional. What that means is I can go k times, and what's it proportional to? This is important. It's proportional to the difference between the temperature of the object and the temperature of couldn't quite circle the whole thing. So it's proportional between the difference of the object and the temperature of its surroundings. So for each of the rest of the problem, it says suppose a metal figurine heated to 150 degrees Fahrenheit is brought into a room having a constant temperature of 72 degrees. So the temperature of its surrounding is 72 degrees. So I'm going to come in here. It's a difference proportional to the difference between the temperature of the object, which we're going to call Y, and the temperature of its surrounding, which we're going to call, which is 72. So what I've got here is, this is not quite that exponential model. It's a little bit different because instead of being dy dt equals k times y, it's dy dt equals k times y minus 72. It's not proportional to the variable itself. It's proportional to the difference between the variable and its surroundings. So we're going to take this model. Let's solve this first to come up with our formula, because this is not that, that exponential growth decay model that we've been using, that y equals CE to the KT. It's actually pretty close to it, and you'll see in a second. So let's go ahead and solve this. So I'm going to times the dt up with the k, and I'm going to divide the y minus 72 with the dy. So I get 1 over y minus 72 equals, oops, I forgot my dy over here, sorry. So I divide the y minus 72 over on the left side with the dy, and I'm timesing the dt on the other side with the k. Okay, integrate both sides. So over here on the left side, that would be the ln of the absolute value of y minus 72. Over on the right side, it would just be kt plus c, plus my constant. Raise e to both sides. So on the left side, I end up with the absolute value of y minus 72. We got to split that apart. Remember, it ends up being a new constant times e to the kt. I'm going to put a plus or minus in front of that. And then plus or minus a constant is just another constant. It's still going to be a constant. So the plus or minus doesn't really matter. Okay, so let's solve for y. So if you look at our new model, it's really close to that exponential growth. The only difference is it's y equals c to the kt plus 72. That's your only difference. So you're looking at it, it's really, really, really close to the model we've already been using. Okay, now that we got our model, now I have to go through and actually answer the question. So C is still the same thing. C is the initial temperature in this case. So the temperature of the object at the beginning. Y is a future temperature, and T is the time. K is that rate, or the rate that it's cooling. It's that constant of proportionality. Okay, so let's read through it and see if we can find some stuff. So it says, suppose a metal figurine is heated to 150 degrees, is brought into a room. So 150 degrees is the temperature at the very beginning. So I'm going to erase this part over here. So that's going to be my C. So I've got y equals 150 e to the kt plus 72. If the figurine cools from 150 to 120 in 15 minutes, how long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit? Okay, so I've got to figure out what K is. And the way you're going to figure out what K is they're always going to give you an example. They're going to give you some information. So it says it cools from 150 to 120 in 15 minutes. So when T equals 15, right, when the time is 15, the new temperature is now at 120 degrees. So that's my T, and that's my Y. So if I plug that in for T and Y over in my formula, I should be able to figure out what K is. So let's do that. I'm going to plug 120 in for Y. So I have 150 e to the k times 15 plus 72. Okay, so let's see if we can get that. I can minus the 72 over here. We're going to go 120 minus 72 is 48 equals 150 e to the 15k. Divide by 150. I'm going to stop there really quick and catch myself. So you guys will have to forgive me. I think I've made a mistake here. I assumed C was the initial 150 degrees temperature. I don't know if that's actually true. So I'm going to backtrack a little bit. I think we're good all the way up to, let's come back down here. Sorry about that. But if I come back down to here, like this is my formula, right? And I've got to figure out what C is. Because of the plus 72, I don't know that C is the actual initial heat as it comes out. But what I do know is this. At time 0, the temperature is 150 degrees. So what I'm going to do, that's T, and that's Y. I'm going to plug those two things in to see if I can solve for C. So I'm going to go 150 equals C times e to the k times t. T is 0, so k times 0 would be 0 plus 72. Hey, e to the 0 is 1, so I get 150 equals c plus 72, right? E to the 0 becomes 1, 1 times c is c, minus a 72 over. So I think c is actually, I don't think, now I know, c is actually equal to 78. So forgive me for that. So let's come down here. Let's write our new model then. And I apologize for that mistake there. If this plus 72 wasn't there, then C will always be the initial value. But because of the plus 72, that changes it. So my actual model is this. And let me do this. Let me slide this work down here. I'm going to put it down here. That's how I figured out what C is. So my actual new model comes out to be Y is equal to, we know what C is. C was 78. 78 e to the kt plus 72. So that's my model right there. Okay, now if I can just figure out what k is equal to, now I have the complete model. That's all I'm missing is just k. So we're going to do the same thing as we did before I realized I'd screwed up there. We're going to plug 15 in for the time and 120 in for the y. So 15 in for the t, 120 for the y. So 120 equals 78 e to the k times 15. So 15k plus 72. And we've got to solve for k. So I'm going to minus the 72 over. 120 minus 72 is 48. 78 e to the 15k. Divide by 78. Take the ln of both sides. So I end up with the ln of 48 divided by 78 equals 15k. Divide by 15. Okay. And that should tell me what k is equal to. Now, like before, this is going to be a decimal. It's probably not a very nice decimal. And so what we're going to do, just like before, is we're just going to store it in our calculator. So grab your calculator and go the ln of 48 divided by 78 divided by 15. And I got a negative 0.03236, so on and so on. And that should make sense, right? K came out to be negative, and the reason why is we talked about this, right? If K is positive, then then your value is growing. If K is negative, then your value is decreasing. Well, this temperature is decreasing, right? You take it out, it's really hot. The room's cooler. It's going to cool off. So it's going to be decreasing. Okay, let's go ahead and store that. So so I'll put this down here, just what it was approximately. K was approximately a negative 0.0323 ... But we're going to store that in the calculator so we can make our answer really accurate. So I'm going to store that as K. So hit the store button. It'll bring up the answer with the arrow, alpha K. And then it should bring up that answer again to show you that it's stored. Okay. A lot of work, right? So we get all that done. I'm going to erase this up over here. You can rewind it if you want to look at that again. Now I have my model. All I have to do is now actually answer the question, which seems like it should be easy, but you'll see in a second you have to do a little bit of work to get this answer. So there's my model, and now I know what K is, right? I've got that value stored in my calculator. So it says, how long will it take for the figurine to reach a temperature of 100 degrees? The reason why this requires a little bit of work, if it gave me the time, I could just plug that in there, plug it all in my calculator, I have my answer. But it gives me the temperature instead. So the temperature is Y. So I want to say, how long does it take until my temperature reaches 100? So now I've got this. So I'll solve this. So minus the 72 over, and we get 28. Divide by 78. So I get 28 over 78 equals e to the kt take the ln of both sides. So I get the ln of 28 divided by 78 equals kt. Divide by k. Remember, we know what k is. It's stored in our calculator. And now we're going to grab our calculator, and we're just going to plug in the ln of 28 divided by 78 divided by k. So let's try that. So ln of 28 divided by 78, and we're going to divide that by k, so alpha k, which we have stored in our calculator. Hit enter, and it comes out to be 31.65255.893. The question says round your answer to the nearest minute on this one. So if it's 31.6, I'm going to round it to 32. So 32 minutes would be our answer. So on most of these problems, if it says it follows the law of exponential growth, you can just use the y equals ce to the kt. If it doesn't say that, then you're going to have to read the problem, and you might have to actually go back and use, solve a differential equation where we have this one, we had dy dt equals k times, and we had t minus, what was it at the beginning? At the very beginning, we had, y minus 72. So dy dt equals k times y, and we had to integrate it to get our function. Now, most of them are going to be pretty similar, right? This one just ended up having that plus 72 on the end, so that can change a little bit. But on most of the problems on your assignment, you'll see it says it follows the law of exponential growth. You don't have to do any calculus at all. You're just using that y equals ce to the kt. Use that formula to set it up and to solve it. Anyway, good luck. Let me know if you got questions.